Hello everyone. Welcome to all my young friends who are studying in intermediate and they are watching this video. My name is Salman, and very recently I created this online platform wherein I posted few demo clips of physics and mathematics, which were in a mixed language, primarily Hindi. But I got a feedback from a lot of you that you wanted it in English. So I am again recording the same demo clips in English so that it serves the purpose of a larger chunk of audience. Henceforth, whatever the courses I am going to upload will be in both the languages, probably simultaneously or maybe with a small lag. Today, we are going to discuss a topic from physics, and the name of the topic is total internal reflection. So let's find out what is total internal reflection. Total internal reflection is a part of a chapter called optics, and total internal reflection is a very interesting natural phenomena. The reason is that we encounter this phenomena at many places in our daily life, which we are going to discuss shortly. So let's try to understand what is total internal reflection. But before that, let us try to refresh some of the knowledge of optics, some of the basic knowledge of optics, one or two terminologies which will be helpful in understanding total internal reflection. So the first terminology is reflection. What do we mean by reflection? Reflection is sending back. That means if a light is striking a surface, returns back, then it is called reflection. This is a surface, for example, this is a surface. The light rays are falling like this and they are sent back like this. So this is called reflection. Then there is one more terminology which is called refraction. What does refraction mean? Refraction means change in direction of a wave passing from one medium to another. Here what we mean by that is, for example, say this is a transparent medium, a glass block. Light strikes on this block. See, the light is rays is striking here. So here the medium is changed. Here the medium is air and here it is glass. So at this interface there is a change in medium. So what we are telling, that change in direction, that means had it gone straight, it would have, these rays would have gone like that. But what the rays do is that they change their direction. You can see here. And again, when they strike at another interface, that means from glass to air, again they change the direction. This is called a refraction. Hope you all must be clear with this, because these are some of the basic things which are taught in 8th, 9th and 10th. But still, I thought it is better to refresh them. Now, when a beam of light strikes another transparent medium, a part is reflected and rest enters the medium. So you may be wondering, okay, why it happens like that. When it is striking a transparent medium, why is it reflected? And only refraction should be there, but it happens like that. And how it happens, I'm just going to demonstrate. For example, this is a glass block, a transparent glass block. A ray is incident on this glass block, a light ray. We draw a normal here. The ray is reflected. This is the reflected ray. And when it enters the medium, it changes the direction. Had it gone straight, it would have gone on this path, but it will change the direction. So this is refracted ray. This is reflected ray. and this is a refracted ray. So both these things, reflection and refraction, they happen simultaneously. Still, do you have a doubt? Anyway, I'll clear that doubt with some beautiful snap, a pictorial depiction. This is a beautiful, snap of a scenery. What can you see here? You can see a fish. Now, fish is in the water, but how are you able to see it? Because the light rays, after refraction, they are reaching fish. And how are you able to see the scenery outside, the reflection of the scenery outside? This you can see. This is because of the reflection of light. The light rays coming from those objects like trees, and the clouds and all those things, they are falling on the surface, and from there they are reflected. That is the reason we are able to see the reflection, and also at the same time we are able to see the refraction. So light is reflected as well as refracted. I hope that this makes it pretty clear to you. Now, you also must have read about Snell's law. That is, a light ray, when it passes from a denser medium to a rarer medium, it bends away from the normal. For example, this is your denser medium and this is your rarer medium. If the light ray is striking like this, you draw a normal. If it goes straight, it would have gone like that. But when it passes from a denser to a rarer, it will bend away from the normal. See, it has gone a bit away from the normal. This is your normal. Again, we are going to depict it with some proper figure. See, this is denser and rarer. Light ray is incident. Now, light ray is going from denser to rarer. We have to draw the normal. This is angle of incidence, which the incident ray makes with normal. Had it gone straight, this dotted line would be its path, but it bends away from the normal. So that means you can see. Now it is clearly visible that this angle is I, this angle is also I. So angle of refraction, this is angle of refraction. It can be easily seen that R is greater than I. Right. So please note this also because it's going to be used. Now, light ray from a denser medium, say water, goes to a rarer medium, say air. Now, this is your denser medium shown in light blue color, and rarer medium here, it is shown in white color. Suppose a ray of light is incident on this surface here. So it is going from denser to rarer medium. So what will happen? This is angle of incidence. Some of it will be refracted, and I told you that both the phenomena happen. So some of it is going to be reflected also. A part is refracted and a part is reflected. Now what we do here, we increase the angle of incidence slowly, gradually and gradually. What will happen? If you increase the angle of incidence, the angle of refraction will also increase. This will be the angle of refraction. You can see here the angle is greater than the angle here. Again, we increase it a bit more. And we keep on increasing till the angle of refraction reaches 90 degree. That means this becomes 90 degree, right? Slowly, we keep on increasing the angle of incidence. Here it was a bit less. Here we again increase it, and we increase it to such an extent that angle of refraction becomes 90 degree. So what happens? You can see that till this, the refracted ray was outside this medium, that is water. But when the angle of refraction becomes pi by 2, that is 90, it is just grazing on the surface, right? The refracted ray grazes on the surface. You must have read this term, grazing. We say cattle are grazing on the field. So when the angle of refraction becomes 90, at that time the angle of incidence is called IC, that is critical angle, right? This is denoted by IC. So you can see in all these three cases, we have drawn three. There can be n number of cases. We can slowly when we'll be increasing I. So there will be many cases. We have only depicted three here just to explain you. In all these three cases, you have refracted ray and reflected ray. Refracted ray, reflected ray. Here also it is refracted. Only thing is it is grazing, and you have reflected ray. So these rays are partially reflected till this position, right? Partially refracted and partially refracted. Now, if we increase the angle of incidence more than this critical angle, what happens? If angle of incidence I is greater than this critical angle, what will happen? Can you guess? Just pause this video and guess. I think some of you might have guessed it correctly. Anyway, I'll clarify what will happen. If the angle of incidence is further increased, no refraction will take place and the incident ray will be totally reflected. Like if I is greater than IC, then there will be no refraction. The whole ray is going to be reflected back in the medium. So here this is case where we have totally reflected ray. This phenomena, when the light is going from a denser to rarer, please remember it is denser to rarer, not rarer to denser. It cannot happen. If it goes from denser to rarer and the angle of incidence is greater than critical angle, then the whole incident ray is totally reflected inside that medium, and this phenomena is called total internal reflection. Now, if we calculate the critical angle by some experiment, we can find the refractive index of the material, because you know that, suppose you must have read in Snell's law, this is medium 1 and this is medium 2. If a light ray is incident here and this is the angle of incidence, and you say this is the angle of refraction. Sin I upon sin R is equal to N2 upon N1, right? That means N2 is refractive index of medium 2, N1 is refractive index of medium 1. We also write it as 1 N2, refractive index of medium 2 with respect to 1. So now in this case, when we have the value of I equal to IC, then what will happen? See, the light when you will have angle of incidence as IC, the refracted ray will graze here and this angle will be 90 degree. This is denser medium and this is rarer medium. So sin IC upon sin R is equal to refractive index of rarer medium upon refractive index of denser medium. This is called NRD, also written as like this, refractive index of rarer medium with respect to denser medium, or it is also written as 1 upon NDR, refractive index of denser medium with respect to rarer medium, right? So in this case, you can clearly see that sin I upon, since sin R is sin 90 degree, is equal to N R D. That means sin IC, and this is equal to 1, sin 90 is equal to N R D, refractive index of rarer with respect to denser, or you can write 1 upon N D R, refractive index of denser medium. So if we calculate by experiment the value of IC, we can know the refractive index of denser medium. So here we are showing some of the refractive indices of some materials which has been calculated like that. So you can see that critical angle in case of water is 48.75 degree, crown glass like this, and these are the refractive index 1.33, 1.52. But the thing which is worth noting here is that refractive index of diamond is the highest, 2.42, and the angle is pretty small, 24.41, means very easily lot of rays are going to be reflected back when they are traveling inside a diamond towards air. So these are refractive index of material with respect to air. So this is the property of diamond which is used to produce glitter. We'll see how. Now you can also find the value of critical angle by a simple experiment using a glass of turbid water and a laser pointer, which you can do at home. Like, say this is a glass having turbid water, and we use laser beam here. And why do you use turbid water? Because laser beam is clearly visible. If you use very clear water, it won't be clearly visible. That is why we are using turbid water, and we can uh, produce this laser beam by a laser pointer which is available at home. Now what will happen? This laser beam, this ray is traveling right now from water towards air, and say if this is the angle of incidence I, if it is greater than critical angle, this ray will be totally internally reflected here, right? So if you keep on changing this angle, just keep on increasing this angle of incidence, you will get a stage when the ray will be reflected back like this, and you can put a paper here and you can see a light spot, red spot here. So the snapshot of experiment is like this. You can see the red mark here on the table itself. But you have to be a bit careful while doing this experiment that please don't point it in your eye because it can be dangerous. Now we come to some examples of this phenomenon which are very interesting and which we encounter in our daily lives. I think many of you, must have seen some of the cases which are being discussed, and some definitely you must have seen in your daily life, like the example which I am going to discuss right now. Shining of air bubbles inside water. You must have seen whenever some air is entrapped and in water and it comes out in the form of bubbles. Uh, it's more seen while we open a cold drink bottle. So what will happen? The air bubble shines. Now, for example, if this is liquid shown in blue color, water, and you have an air bubble here. This is an air bubble. Now, now light is going to fall on this air bubble from all direction, like this, like this, like this. But there will be certain rays of light where they will be falling on this bubble and having the angle of incidence more than the critical angle. For example, consider this ray. Now, for example, you draw normal here. If this angle I is greater than IC, now the light is going from a denser to rarer. Only then this phenomena will take place. Please note that it will never take place if the light is going from rarer to denser. Only from denser to rarer. Here we can see it is traveling from water to air. That means denser to rarer. If the angle of incidence is greater than critical angle, then this is going to be totally internally reflected back like this. And this part of the bubble is going to shine. If you see the snap of bubbles, you can see these shine which you are seeing in bubble. This is only because of total internal reflection. Let's take one more example. A more interesting example. Phenomena of mirage. We read it as mirage, but we write it as mirage. But pronunciation is mirage. Mirage is an optical illusion. You see what is not there, and it happens predominantly in deserts during hot summer days. Even you can see it in cities. I'll just show you how. But it's an optical illusion, and the reason is total internal reflection. Now let me explain you how it happens. For example, this is ground. You are standing in a place which is very hot, say desert itself, and you have a tree here. Now rays from tree, from any point of object, emanate out in all directions. Now, for example, one ray from the top of the tree comes out like this, and my observer is here. So he'll see the top of the tree when the light ray from top strikes his eye. What happens? The layer which is near the earth becomes very hot because the ground is very hot. So this becomes rarer medium, and over and above that layer is a denser medium, because the layer above is not that hot. Normally what happens in normal circumstances, if the layer has a density d1, d2, d3, so the denser thing will be at the bottom. That means d1 will be greater than d2, will be greater than d3. But in case of summers, the layer which is just adjacent to the ground becomes very hot, and it becomes a rarer medium, and over that there is a denser medium. Actually, in fact, there will be many layers. I have only drawn one layer just for explaining you. There will be many layers where you will have rarer and more denser and more denser and more denser, like that. Now suppose from the same point another light ray comes like this. So now this light ray, when it reaches the ground and a lot of layers are there, and with decreasing density, then the light is moving from denser to rarer. So what will happen? Suppose at this place it encounters the first layer, so it will bend away from the normal like this when it is going from denser to rarer medium. So it will bend away. Again, in another layer, it will again bend away like that. And say there is one layer where this angle is more than critical angle. Then this layer will be totally reflected back, and it will reach the eye like this. Now this ray is coming from the top, but it appears to be coming like this way. So it appears to be coming from, say, beneath the ground. So if you trace this ray to ground, it will appear that ray is coming from this point. That means the image of the tree will be formed, inverted image is going to be formed like this. So you will have an illusion. That means you may think, when this kind of image form, we think that there is a water there. Actually, water is not there, but this is an optical illusion. Just see a snapshot of optical illusion in desert. So this is mirage in desert. In desert it happens, the people who very frequently travel in deserts, especially during summer days, they see this kind of illusion. And these kinds of phenomena have a very negative bearing on animals like deer and all those animals. When they see these kind of illusion, they think that there is water there, and they run towards that with their full energy, because they are thirsty. And when they go there and find that there is no water, then they die out of a shock. You can also see this phenomena, or you might have seen in your cities when you travel on highway like this. The bitumen road is quite hot, and the layer of air near it becomes hot, and hence it serves as a rarer medium. One more example, and that is the phenomena of Looming. This phenomena is also an optical illusion. You see what is not there, and this happens predominantly in cold regions. In fact, it happens in very, very cold regions. It is, something reverse of, that mirage. In mirage, you see the image downwards, but here you see the image hanging midway in the air. How does it happen? What happens that, say, if this is our Earth and this is a sea, probably, where it's frozen or it's very, very, very cool. Suppose there is a ship and this is the line of sight, and my observer is here, stationed here. So right now, since there is obstruction here, so he can't see the ship because ship is too far from him. But what happens? The light rays from ship, emit in every direction. But because of the air being very cold here, this is the air adjacent to sea is very cold. And as you move up, the air becomes hot, less cold, warmer air. So there are some warm air layers, and beneath them there are cold air layers. So when the light ray, so this is a rarer medium and this is a denser medium. So when the light ray, any light ray, say for example, it comes out of this point. So what happens? There will be many layers, as I told you. This is not, one layer I have only, shown for the sake of demonstration. There will be many, many layers. And this light ray is going from denser to rarer. So it will bend away from the normal, again away from the normal. And in some layer, the angle will be more than the critical angle. So here it will be reflected. Total internal reflection will take place. So what will happen? It will reach observer eye, and the ray is coming from ship, but it will appear that it is coming from, you just extend it backwards like this. So this will be the image of ship, although ship is in the sea, which is not seen directly by the observer, but it will appear that this ship is hanging midway in air. This phenomena is called looming, and you can see there's some snapshot of looming. You can see the ship which is very far, which is not seen by the observer who is standing on the beach. So it is beyond the line of sight, but because of this phenomena of total internal reflection, it appears that to be hanging midway in air. One more quite interesting example is sparkling of diamond. I just told you that diamonds sparkle because the critical angle is very less. It is 24.4 degrees only. Now let me draw the diagram of a diamond. Say, for example, if the light rays, a beam of light strikes diamond, it goes inside. Now this ray is traveling from inside diamond and coming out of here. That means denser to rarer medium. So here total internal reflection can take place if this angle is greater than angle of critical angle. Now then this whole beam is going to be reflected, and at this surface also, if the angle of incidence is greater than critical angle, again it is going to be reflected, and it comes out as glitter. This is the reason why diamond glitters. One more important thing is diamond found in nature, they do not exhibit this kind of brilliance. But when cutting is done on diamond, when cutters do that cutting, it is cut in such a manner that multiple total internal reflection takes place. That is the reason diamonds glitter. But if you know, uh, see a diamond which has been just taken from a diamond ore, you will find there is very, very less or nearly nil glitter in that. But when the diamond is cut in such a manner that multiple total internal reflection take place, and here we take the help of critical angle because it's so less, very easily total internal reflection can take place. So you can see sparkling of a diamond. It sparkles so beautifully. You must have seen that. Now let's try out some problem on total internal reflection. Now the problem says a small bulb is placed at the bottom of a tank containing a liquid to a depth of 80 centimeter. What is the area of surface of water through which light from the bulb can emerge out? The refractive index of liquid is given as under root 2. Now if you read the question, that means only some portion of the light comes out. That is being said in the question. You can easily make out that this is a question of total internal reflection. Now let's analyze the question. Let's visualize the problem. For example, it is being told that there is a small bulb at the bottom of a tank containing liquid. Say if there is no liquid, then what happens? Tank is empty. This is 80 centimeter is the depth and there is a bulb here. If there is no liquid, light will just come out like this. But if the tank is filled with liquid like this, then what will happen? Some of the rays which are coming from denser to rarer will come out, will bend away from the normal and come out like this. But and some rays where they just reach the critical angle, this is IC, will just graze on the surface like the ray on the right and the ray on the left, which I have shown in brown color. But what happens to these rays? In these cases, the angle of incidence, either this or this, both is greater than critical angle. Similar for these two rays. So for this ray, this ray, this ray, and this ray, they will be reflected back. I am only drawing few rays, you can't count them. So they will be reflected back like this. So what will we see? We'll see a shining surface like this. So I am telling you a shining surface, but here I am only drawing a line. So please don't get confused. I'll again explain this problem in 3D. In fact, this is going to be a conical shape. A conical shape. This shape will be conical. I'll show you how. So let's visualize the problem in 3D. Before solving that, this is the bulb. The light comes out, and this is the cone. And from here, the light grazes on the surface, like this, and you can see the shining surface like this. Although since it's a three-dimensional figure, the shape is seen as an ellipse, but it's a circular shape. The shape is circle, right? Say of radius 1. I hope you are able to visualize the problem properly. Now let's solve the problem. So this is 80 centimeter is the depth. This is the ray, which will have angle of incidence as critical angle, and beyond this all rays are going to be reflected back, and the rays which are emerging out of this region, they will be responsible for the shining and they will go out of the liquid. Okay, so if this is IC, this angle is also IC, because these two lines are perpendicular to the surface and they are parallel hence. So that means sine IC upon this angle is pi by 2 sine pi by 2 as per Snell's law. This is equal to 1 upon refractive index of the material, which is given as under root 2. Now sine pi by 2 is equal to 1. That means sine IC is equal to 1 upon root 2. We'll just write here and erase all. Sine IC is equal to 1 upon under root 2. Now again, from this triangle, this is R and this side is 80. So this hypotenuse is under root R square plus 0.8 whole square, because we have converted it into meter. It's in centimeter. So sine IC is also equal to R upon under root R square plus 0.64. Now this is equation 1 and this is equation 2. You can equate both of them. 1 upon under root 2 is equal to R upon under root R square plus 0.64. Now square and cross multiply. That means 2R square is equal to R square plus 0.64. That means R square is equal to 0.64. Now they require the area. So area of the surface which is shining, that is equal to pi R square, because it's a circle. If we take the value of pi as 3.14 and R square is 0.64, so this comes out to be roughly 2 meter square. So let's check the answer, and the answer is 2 meter square. So I hope this is clear to you, and most of the questions which are asked in total internal reflection are nearly similar to this. So if you have understood this question, you will be able to solve them very easily. Please try out some questions from your book. So this is all in total internal reflection. Hope you are clear with this topic of total internal reflection and you found this video interesting. So if you like this video, please show your likes on YouTube, and do subscribe to this channel and don't forget to press the bell icon so that you can get all the updates, regular updates, and do share it with your friends. And thanks for watching this video. Have a nice day.